In physics, thermal conductivity is the property of a material to conduct heat. It is evaluated primarily in terms of Fourier's law for heat conduction. Heat transfer occurs at a higher rate across materials of high thermal conductivity than across materials of low thermal conductivity. Correspondingly, materials of high thermal conductivity are widely used in heat sink applications and materials of low thermal conductivity are used as thermal insulation. Thermal conductivity of materials is temperature dependent. The reciprocal of thermal conductivity is called thermal resistivity. Units of thermal conductivity: in SI units, thermal conductivity is measured in watts per meter Kelvin. The dimension of thermal conductivity is M1L1 tar3IA1. These variables vary mass, length, time, and temperature. In imperial units, thermal conductivity is measured in British thermal units (RFTA) a degree Fahrenheit. Other units which are closely related to the thermal conductivity are in common use in the construction and textile industries. The construction industry makes use of units such as the R value and the U value. Although related to the thermal conductivity of a material used in an insulation product, R and U values are dependent on the thickness of the product. Likewise, the textile industry has several units including the TOG and the CLO which express thermal resistance of a material in a way analogous to the R values used in the construction industry. Measurement. There are a number of ways to measure thermal conductivity. Each of these is suitable for a limited range of materials, depending on the thermal properties and the medium temperature. There is a distinction between steady-state and transient techniques. In general, steady-state techniques are useful when the temperature of the material does not change with time. This makes the signal analysis straightforward. The disadvantage is that a well-engineered experimental setup is usually needed. The divided bar is the most common device used for consolidated rock solids. Experimental values. Thermal conductivity is important in material science, research, electronics, building insulation and related fields, especially where high operating temperatures are achieved. Several materials are shown in the list of thermal conductivities. These should be considered approximate due to the uncertainties related to material definitions. High energy generation rates within electronics or turbines require the use of materials with high thermal conductivity such as copper, aluminium, and silver. On the other hand, materials with low thermal conductance, such as polystyrene and alumina, are used in building construction or in furnaces in an effort to slow the flow of heat, that is for insulation purposes. Definitions. The reciprocal of thermal conductivity is thermal resistivity, usually expressed in Kelvin meters per watt. For a given thickness of a material, that particular construction's thermal resistance and the reciprocal property, thermal conductance, can be calculated. Unfortunately, there are differing definitions for these terms. Conductance. For general scientific use, thermal conductance is the quantity of heat that passes in unit time through a plate of particular area and thickness when its opposite faces differ in temperature by 1 Kelvin. For a plate of thermal conductivity K, area A and thickness L, the conductance calculated is kilooampere per liter, measured in Watt R1. The thermal conductance of that particular construction is the inverse of the thermal resistance. Thermal conductivity and conductance are analogous to electrical conductivity and electrical conductance. There is also a measure known as heat transfer coefficient, the quantity of heat that passes in unit time through a unit area of a plate of particular thickness when its opposite faces differ in temperature by 1 Kelvin. The reciprocal is thermal insulance. In summary, thermal conductance equals kilooampere per liter, measured in Watt R1. Thermal resistance equals L/kilooampere, measured in kW1. Heat transfer coefficient equals KL, measured in Watt R1. R2. Thermal insulance equals LK, measured in km2 or Wa1. The heat transfer coefficient is also known as thermal admittance in the sense that it may be seen as admitting heat to flow. Resistance. Thermal resistance is the ability of a material to resist the flow of heat. Thermal resistance is the reciprocal of thermal conductance, that is, lowering its value will raise the heat conduction and vice versa. When thermal resistances occur in series, they are additive. Thus, when heat flows consecutively through two components each with a resistance of 3 degrees Celsius W, the total resistance is 3 plus 3 equals 6 degrees Celsius W. A common engineering design problem involves the selection of an appropriate-sized heat sink for a given heat source. Working in units of thermal resistance greatly simplifies the design calculation. The following formula can be used to estimate the performance. Where RHS is the maximum thermal resistance of the heat sink to ambient, in a degree Celsius W, IT is the required temperature difference, in a degree Celsius, PTH is the thermal power, in watts, RS is the thermal resistance of the heat source, in a degree Celsius W. For example, if a component produces 100 W of heat, and has a thermal resistance of 0.5 degrees Celsius W, what is the maximum thermal resistance of the heat sink? Suppose the maximum temperature is 125 degrees Celsius, and the ambient temperature is 25 degrees Celsius. Then IT is 100 degrees Celsius. The heat sink's thermal resistance to ambient must then be 0.5 degrees Celsius W or less. Transmittance, a third term, thermal transmittance, quantifies the thermal conductance of a structure along with heat transfer due to convection and radiation. It is measured in the same units as thermal conductance and is sometimes known as the composite thermal conductance. The term U-value is often used. Admittance, the thermal admittance of a material, such as a building fabric, is a measure of the ability of a material to transfer heat in the presence of a temperature difference on opposite sides of the material. Thermal admittance is measured in units of watts per unit area per temperature change. Thermal admittance of a building fabric affects a building's thermal response to variation in outside temperature. Influencing factors, temperature. The effect of temperature on thermal conductivity is different for metals and nonmetals. In metals, conductivity is primarily due to free electrons. Following the Wiedemann-Eurofranz law, thermal conductivity of metals is approximately proportional to the absolute temperature times electrical conductivity. In pure metals, the electrical conductivity decreases with increasing temperature and thus the product of the two, the thermal conductivity, stays approximately constant. In alloys, the change in electrical conductivity is usually smaller and thus thermal conductivity increases with temperature, often proportionally to temperature. On the other hand, heat conductivity in known metals is mainly due to lattice vibrations. Except for high-quality crystals at low temperatures, the Phonon mean free path is not reduced significantly at higher temperatures. Thus, the thermal conductivity of known metals is approximately constant at low temperatures. At low temperatures well below the debut temperature, thermal conductivity decreases, as does the heat capacity. Chemical phase. When a material undergoes a phase change from solid to liquid or from liquid to gas, the thermal conductivity may change. An example of this would be the change in thermal conductivity that occurs when ice at 0 degrees Celsius melts to form liquid water at 0 degrees Celsius. Thermal anisotropy. Pure crystalline substances can exhibit different thermal conductivities along different crystal axes, due to differences in Phonon coupling along a given crystal axis. Sapphire is a notable example of variable thermal conductivity based on orientation and temperature, with 35 with Mach A along the C-axis and 32 with Mach A along the A-axis. Electrical conductivity. In metals, thermal conductivity approximately tracks electrical conductivity according to the Wiedemann-Eurofranz law, as freely moving valence electrons transfer not only electric current but also heat energy. However, the general correlation between electrical and thermal conductance does not hold for other materials, due to the increased importance of Phonon carriers for heat in nonmetals. Highly electrically conductive silver is less thermally conductive than diamond, which is an electrical insulator, but due to its orderly array of atoms it is conductive of heat via phonons. Magnetic field. The influence of magnetic fields on thermal conductivity is known as the Ricard-Leduc effect. Convection. Air and other gases are generally good insulators, in the absence of convection. Therefore, Many insulating materials function simply by having a large number of gas-filled pockets which prevent large-scale convection. Examples of these include expanded and extruded polystyrene and silica aerogel. Natural, biological insulators such as fur and feathers achieve similar effects by dramatically inhibiting convection of air or water near an animal's skin. Light gases, such as hydrogen and helium, typically have high thermal conductivity. Dense gases such as xenon and dichlorodifluoromethane have low thermal conductivity. An exception, sulfur hexafluoride, a dense gas, has a relatively high thermal conductivity due to its high heat capacity. Argon, a gas denser than air, is often used in insulated glazing to improve their insulation characteristics. Physical origins. Heat flux is exceedingly difficult to control and isolate in a laboratory setting. At the atomic level, there are no simple, correct expressions for thermal conductivity. Atomically, the thermal conductivity of a system is determined by how atoms composing the system interact. There are two different approaches for calculating the thermal conductivity of a system. The first approach employs the Green-Kipper relations. Although this employs analytic expressions, which, in principle, can be solved, calculating the thermal conductivity of a dense fluid or solid using this relation requires the use of molecular dynamics computer simulation. The second approach is based on the relaxation time approach. Due to the anharmonicity within the crystal potential, the phonons in the system are known to scatter. There are three main mechanisms for scattering: boundary scattering, a phonon hitting the boundary of a system; mass defect scattering, a phonon hitting an impurity within the system and scattering; phonon-phonon scattering, a phonon breaking into two lower energy phonons or a phonon colliding with another phonon and merging into one higher energy phonon. Lattice waves. Heat transport in both amorphous and crystalline dielectric solids is by way of elastic vibrations of the lattice. This transport mode is limited by the elastic scattering of acoustic phonons at lattice defects. These predictions were confirmed by the experiments of Chang and Jones on commercial glasses and glass ceramics, where the mean free paths were limited by internal boundary scattering to length scales of 10^2 cm to 10^3 cm. The phonon mean free path has been associated directly with the effective relaxation length for processes without directional correlation. If VGA is the group velocity of a phonon wave packet, then the relaxation length is defined as where T is the characteristic relaxation time. Since longitudinal waves have a much greater phase velocity than transverse waves, long is much greater than VTRANS, and the relaxation length or mean free path of longitudinal phonons will be much greater. Thus, thermal conductivity will be largely determined by the speed of longitudinal phonons. Regarding the dependence of wave velocity on wavelength or frequency, low-frequency phonons of long wavelength will be limited in relaxation length by elastic Rayleigh scattering. This type of light scattering from small particles is proportional to the fourth power of the frequency. For higher frequencies, the power of the frequency will decrease until at highest frequencies scattering is almost frequency independent. Similar arguments were subsequently generalized to many glass-forming substances using Brillouin scattering. Phonons in the acoustical branch dominate the phonon heat conduction as they have greater energy dispersion and therefore a greater distribution of phonon velocities. Additional optical modes could also be caused by the presence of internal structure at a lattice point. It is implied that the group velocity of these modes is low and therefore their contribution to the lattice thermal conductivity IL is small. Each phonon mode can be split into one longitudinal and two transverse polarization branches. By extrapolating the phenomenology of lattice points to the unit cells, it is seen that the total number of degrees of freedom is 3pq when p is the number of primitive cells with q atoms unit cell. From these only 3p are associated with the acoustic modes, the remaining 3p, q1, are accommodated through the optical branches. This implies that structures with larger p and q contain a greater number of optical modes and a reduced IL. From these ideas, it can be concluded that increasing crystal complexity, which is described by a complexity factor Cf, decreases IL. Michaeline Rufos and P. G. Clemens derived the exact proportionality in their article Thermal Conductivity of Complex Dielectric Crystals at Phys. Rev. B7, 5379 Euro 5386. This was done by assuming that the relaxation time I decreases with increasing number of atoms in the unit cell and then scaling the parameters of the expression for thermal conductivity in high temperatures accordingly. Describing of anharmonic effects is complicated because exact treatment as in the harmonic case is not possible and phonons are no longer exact Huygens solutions to the equations of motion. Even if the state of motion of the crystal could be described with a plane wave at a particular time, its accuracy would deteriorate progressively with time. Time development would have to be described by introducing a spectrum of other phonons, which is known as the Phonon decay. The two most important anharmonic effects are the thermal expansion and the Phonon thermal conductivity. Only when the Phonon number Euro to the first null Euro deviates from the equilibrium value Euro to the first null 0 euros, can a thermal current arise as stated in following expression, where v is the energy transport velocity of phonons. Only two mechanisms exist that can cause time variation of Euro to the first null Euro in a particular region. The number of phonons that diffuse into the region from neighboring regions differs from those that diffuse out, or phonons decay inside the same region into other phonons. A special form of the Boltzmann equation states this. When steady-state conditions are assumed, the total time derivative of Phonon number is zero, because the temperature is constant in time and therefore the Phonon number stays also constant. Time variation due to Phonon decay is described with a relaxation time approximation, which states that the more the Phonon number deviates from its equilibrium value, the more its time variation increases. At steady-state conditions and local thermal equilibrium are assumed, we get the following equation. Using the relaxation time approximation for the Boltzmann equation and assuming steady-state conditions, the Phonon thermal conductivity IL can be determined. The temperature dependence for IL originates from the variety of processes, whose significance for IL depends on the temperature range of interest. Mean free path is one factor that determines the temperature dependence for IL, as stated in the following equation, where I is the mean free path for phonon and denotes the heat capacity. This equation is a result of combining the four previous equations with each other and knowing that for cubic or isotropic systems and at low temperatures the anharmonic interaction does not influence the mean free path and therefore, the thermal resistivity is determined only from processes for which Q conservation does not hold. These processes include the scattering of phonons by crystal defects, or the scattering from the surface of the crystal in case of high-quality single crystal. Therefore, thermal conductance depends on the external dimensions of the crystal and the quality of the surface. Thus, temperature dependence of IL is determined by the specific heat and is therefore proportional to T3. Phonon quasi-momentum is defined as AQ and differs from normal momentum due to the fact that it is only defined within an arbitrary reciprocal lattice vector. At higher temperatures, the conservation of energy and quasi-momentum, where Q1 is wave vector of the incident phonon and Q2, Q3 are wave vectors of the resultant phonons, may also involve a reciprocal lattice vector G complicating the energy transport process. These processes can also reverse the direction of energy transport. Therefore, these processes are also known as umklapp processes and can only occur when phonons with sufficiently large Q vectors are excited, because unless the sum of Q2 and Q3 points outside of the Brillouin zone the momentum is conserved and the process is normal scattering. The probability of a phonon to have energy is given by the Boltzmann distribution. To U process to occur the decaying phonon to have a wave vector Q1 that is roughly half of the diameter of the Brillouin zone, because otherwise quasi-momentum would not be conserved. Therefore, these phonons have to possess energy of, which is a significant fraction of dB energy that is needed to generate new phonons. The probability for this is proportional to, with temperature dependence of the mean free path has an exponential form. The presence of the reciprocal lattice wave vector implies a net phonon backscattering and a resistance to phonon and thermal transport resulting finite IL, as it means that momentum is not conserved. Only momentum non-conserving processes can cause thermal resistance. At high temperatures the mean free path and therefore IL has a temperature dependence τ1, to which one arrives from formula by making the following approximation and writing. This dependency is known as Euclid's law and originates from the temperature dependency of the probability for the U process to occur. Thermal conductivity is usually described by the Boltzmann equation with a relaxation time approximation in which Phonon scattering is a limiting factor. Another approach is to use analytic models or molecular dynamics or Monte Carlo-based methods to describe thermal conductivity in solids. Short wavelength phonons are strongly scattered by impurity atoms if an alloyed phase is present, but mid and long wavelength phonons are less affected. Mid and long wavelength phonons carry significant fraction of heat, so to further reduce lattice thermal conductivity one has to introduce structures to scatter these phonons. This is achieved by introducing interface scattering mechanism, which requires structures whose characteristic length is longer than that of impurity atom. Some possible ways to realize these interfaces are nanocomposites and embedded nanoparticle structures. Electronic thermal conductivity: hot electrons from higher energy states carry more thermal energy than cold electrons, while electrical conductivity is rather insensitive to the energy distribution of carriers because the amount of charge that electrons carry does not depend on their energy. This is a physical reason for the greater sensitivity of electronic thermal conductivity to energy dependence of density of states and relaxation time, respectively. Mayan and Sofo 7436-7439 showed that materials with a certain electron structure have reduced electron thermal conductivity. Based on their analysis one can demonstrate that if the electron density of states in the material is close to the delta function, the electronic thermal conductivity drops to zero. By taking the following equation, where I0 is the electronic thermal conductivity when the electrochemical potential gradient inside the sample is zero, as a starting point. As next step the transport coefficients are written as following. Where and AO the Bohr radius. The dimensionless integrals in are defined as, where S, x, is the dimensionless transport distribution function. The integrals in are the moments of the function, where x is the energy of carriers. By substituting the previous formulas for the transport coefficient to the equation for IE we get the following equation. From the previous equation we see that IE to be 0 the bracketed term containing in terms have to be 0. Now if we assume that, where I is the Dirac delta function, in terms get the following expressions. By substituting these expressions to the equation for IE, we see that it goes to 0. Therefore, P, x, has to be delta function. Equations. In an isotropic medium the thermal conductivity is the parameter K in the Fourier expression for the heat flux. Where is the heat flux in the temperature gradient? The sign in the expression is chosen so that always K greater than 0 as heat always flows from a high temperature to a low temperature. This is a direct consequence of the second law of thermodynamics. In the one-dimensional case Q equals HA with H the amount of heat flowing per second through a surface with area A and the temperature gradient is dt dx so. In case of a thermally insulated bar in the steady state H is constant. If A is constant as well the expression can be integrated with the result. Where TH and TL are the temperatures at the hot end and the cold end respectively, and L is the length of the bar. It is convenient to introduce the thermal conductivity integral. The heat flow rate is then given by. If the temperature difference is small k can be taken as constant. In that case, simple kinetic picture. In this section we will derive an expression for the thermal conductivity. Consider a gas with a vertical temperature gradient. The upper side is hot and the lower side cold. There is a downward energy flow due to the fact that the gas atoms, going down, have a higher energy than the atoms going up. The net flow of energy per second is the heat flow h. The heat flow is proportional to the number of particles that cross the area A per second. This number is proportional to the product NVA where n is the particle density and v the mean particle velocity. The magnitude of the heat flow will also be proportional to amount of energy transported per particle so with the heat capacity per particle C in some characteristic temperature difference IT. So far we have The unit of H is JS and of the right-hand side at IS a eurocent, m, car eurocent particle a eurocent, m2, a eurocent, k, equals JS, so this is already of the right dimension. Only a numerical factor is missing. For IT we take the temperature difference of the gas between two collisions, where L is the mean free path. Detailed kinetic calculations show that the numerical factor is -1/3, so, all in all. Comparison with the one-dimension expression for the heat flow, given above, gives as the final result. The particle density and the heat capacity per particle can be combined as the heat capacity per unit volume, so where CV is the molar heat capacity at constant volume and Bm the molar volume. For an ideal gas the mean free path is given by where I Florin is the collision cross-section. So the heat capacity per particle C and the cross-section I Florin both are temperature independent, so the temperature dependence of K is determined by the T dependence of V. For a monatomic ideal gas, with atomic mass m, V is given by so. This expression also shows why gases with a low mass have a high thermal conductivity. For metals at low temperatures the heat is carried mainly by the free electrons. In this case the mean velocity is the Fermi velocity, which is temperature independent. The mean free path is determined by the impurities and the crystal imperfections, which are temperature independent as well. So the only temperature dependent quantity is the heat capacity C, which, in this case, is proportional to T, so with Ko a constant. For pure metals such as copper, silver, etc. L is large, so the thermal conductivity is high. At higher temperatures the mean free path is limited by the phonons, so the thermal conductivity tends to decrease with temperature. In alloys the density of the impurities is very high, so L and, consequently K, are small. Therefore alloys, such as stainless steel, can be used for thermal insulation. See also References, Notes. References. Further reading, Callister, William. Appendix B. Materials Science and Engineering, An Introduction. John Wiley & Sons. PA 757. ISBN A0-471-22471-5. Halliday, David. Rusnick, Robert. And Walker, Jill, 1997. Fundamentals of Physics. John Wiley & Sons, New York, ISBN 0-471-10558-9. Srivastava G.P., A Physics of Phonons. Adam Hilger, IOP Publishing Limited, Bristol. TM 5-852-6 AFR 88-19, Volume 6, Reed, C.R., Prausnitz, J.M., Polling B.E., Properties of Gases and Liquids, 4 edition, M.C. Graw-Hill, 1987, R. Jovan, R. Das, A. Ahmed, P. Rutz B. Javan, B. Miney, Thermal Properties of Carbon Fiber Epoxy Composites with Different Fabric Weaves, in SAMPE International Symposium Proceedings, Charleston, South Carolina. 2012, external links, Air Thermal Conductivity Calculator, Thermopedia J. Chemphys Thermal Conductivity of Electrolyte Solutions, J. Chemphys Gas Mixtures.